Welcome to the Jack Westin MCAT podcast with your hosts, Michael Maleka
and Molly Hudash. Hello, everyone, and welcome back to the Jack Westin MCAT podcast with your hosts, Mike and Molly. Mike, I'm super excited about this episode because we are coming hot out of acids and bases. And today we're talking about something that is not really that related, and yet students get them mixed up
all the time. I think because there's one piece that kind of looks similar in both, but I think I like this thing that we're doing where we're kind of hitting the reactions that are really foundational, right? We talked very generally. We had this kind of series on like homeostasis, right? We talked about keeping equilibrium, and then acids and bases fit in really well. But then another reaction that's so important, that's so yield, and kind of serves a similar role like acids and bases, where I think in itself it's not the most, there's not so much content on just thing, but you see its application everywhere so much, especially in, things like metabolism. So redox reactions are something that are so high yield, right, on this exam, and something, I'm really excited to talk about today with you.
Yes. So in case you missed it, redox is our topic.
Oh, I thought you already introduced that. Did I
actually didn't.
I thought you were like, oh yeah, we already know we're talking about redox. So I just like it in. Oh,
I feel like I should have.
Yeah.
People are like, what are they talking about? We're talking about
redox reactions, right,
which stands for, it's a nice little mashup word of reduction and oxidation. Terms that you may have heard before, especially with little mnemonics like LEO-GER or oil rig, right? But it's this idea where you have two molecules that have this transfer of electrons going on. One is losing electrons, one is gaining. And we kind of alluded to this a little bit in the acids and bases episode that we just completed, right? Which was, we have this transfer of a proton, and we have in an acid and a base situation, right? A base is donating two electrons, to form a new bond with the proton, right? In that case, the base is reaching out with its little electron arms and grabbing onto a proton. There's no transfer of electrons in that case. It's more that the base is taking its own electrons and establishing a bond with them. It's using those electrons for something rather than one thing loses electrons and those electrons are transferred to something else. So we'll talk a lot about this over the next couple minutes.
More than a couple, but
probably maybe a few.
Maybe more than a couple, yeah.
But this information, like you mentioned, is applicable in so many different contexts, right? Of course, in general chemistry, where we originally learned this material, but it also connects to other topics beyond just redox, right? Electrochemistry is all redox, and a ton of things in biochem as well, right? Metabolism, there are tons and tons of redox reactions, especially in our electron transport chain.
Oh, electron, that's a funny word that I think is pretty relevant, right?
Being transported.
Okay.
Chain. Yes, that is a huge wave of redox reactions. So this episode is really going to set the foundation for future episodes as well. We'll cover the basics, but we are going to continue to build on this material in several other episodes that we have on deck coming up pretty soon.
Absolutely. So I think it's great if we just start from the very, very basics, right? Let's start from the beginning. So we've talked about, transferring protons, like protons being given away, protons being picked up. Here, we're not talking about like now protons being given away and protons being picked up, but electrons being given away and electrons being given up. In the molecular world, there's this reaction where one atom or molecule can essentially give its electrons to another atom or molecule. When an atom molecule gains electrons, we say that molecule or atom has been reduced, right? Because when we talk about reduction, right, that's how it's defined. When you gain electrons, you reduce. I always and we'll have a mnemonic for this in a second, but I always say gaining electrons, reduce, GER. Then, well, if something's gained electrons, well, therefore something else must have lost those electrons as well. Right? And so when you lose electrons, we call that oxidation, right? And these are the kind of two halves of our redox, reduction, oxidation reaction. One's reduced and one's oxidized. And what's kind of really critical to see here is that you can never ever, ever, ever have a reduction without an oxidation and vice versa. You can never, these reactions can't happen on their own. They always, always happen in pairs.
Mm-hmm. Yeah, it's like if you can't just suddenly materialize an electron out of nowhere,
Hmm.
right? We don't just suddenly create electrons. So if
Hmm.
something is gaining an electron, it has to come from somewhere,
Hmm.
right? We don't have little electron factories that we just build this stuff, right? It
Okay.
has to come from somewhere.
Hmm.
Um, and I like that you're hinting at the mnemonic that we talk about in case
Hmm.
anyone's like, how am I supposed to
How do I
remember if I
remember that? Is that memorizing thing? Yeah. Hmm.
I was always a LEO-GER girl,
So
right?
was I. So I'm a
Oh my
Leo
gosh,
girl. I'm a
I
Leo.
was gonna ask.
No, I
Losing
was a,
electrons means you're oxidized. Gaining electrons means you're reduced. It flows off the tongue. You got a
right,
little
right.
lion in your
Right.
head growling at you.
Absolutely.
We
Right. Not
love
my
it.
stomach, it's whatever. But yeah, Leo, Leo, losing electrons, oxidation, GER, gaining electrons, reduction. I always think Leo-GER, but it's so funny every time I speak about it, everyone else loves the other one.
Oil rig. I
Oil rig.
know.
I'm like, well, I never learned
Why?
oil rig growing up. I only started
I
learning
mean,
about oil rig when I did MCAT things, and I was like, what?
yeah. I mean,
Mhm.
I actually feel very strongly that Leo goes GER, so losing electrons means you're oxidized, gaining electrons means you're reduced, is superior to oil rig, which
Ooh.
is oxidation is losing, reduction is gaining. Because
Mm.
that is not specific enough. If we thought
Right.
of what we talked about before about Bronsted-Lowry acids and bases,
Hmm.
you might think oxidation is losing protons.
Oh, I mean, I
Reduction
guess
is gaining
yeah, it's
protons.
not
There's
specific enough.
nothing
Hmm.
it's not telling you,
Hmm.
it's not helping you figure out what's actually going on with reduction and
Hmm. Hmm.
oxidation,
Hmm.
right? So I love LEO-GER because you've got the
Same.
E, you've got the electron part of it.
Hmm.
Um, I don't see that super often, students mixing up oil rig with, acids bases, but it's possible, right?
Hmm.
If you're choosing between two, LEO-GER.
This is a
I think it's superior.
this is a Leo goes Gur super
Yeah,
like
we're a fan club of
we are a
LEO-GER.
fan of Club of Leo goes Gur. You'll
We
never
are
see oil
probably
rig here.
outnumbered.
Yeah, well, absolutely. Whenever I talk about it, like in like one of our free trial sessions or any one of my classes, like it's always like I'm like, oh, what mnemonic do we use? Everyone uses oil rig, and I'm like,
Oil rig.
oh, I actually like Leo goes Gur, but that's whatever.
And they're like, loser.
Literally loser. I'm like,
I'm like
nice,
wiping a
thanks.
tear. No big
Thanks.
deal.
No, that's whatever. So yeah,
Yeah.
so again, so these reactions always have in pair. Something's losing, something's gaining. And I think here is a really good time to talk about something I see confused way too often, right? The
Yes.
idea of reducing agents and
Yes.
oxidizing agents. Oh my goodness, this freaks me out because I'm always like, I see it. It's one of those kind of topics that you constantly see it mixed up all the time. So let's clear the room. Let's figure it out right now what each means. Okay.
Yes.
So, reducing agent. I always think if I'm an agent, I'm doing this thing to somebody else, right? If I'm
Hmm.
a reducing agent, I'm an agent. I make the change. I reduce something else. But therefore, if I am reducing something else, what's happening to me?
If you're supplying electrons to reduce something else, GER, right? Then
Mhm.
you must be losing those electrons. You must be
Exactly.
giving them to somebody else.
Those electrons have to be coming from me. A reducing agent reduces something else. And the way I always think about it, like, well, reduction can't happen on its own, so therefore something
Mhm.
else must be being oxidized. So if that thing's being reduced, I'm getting oxidized. Exact opposite for an oxidizing agent. If I'm an oxidizing agent, I am an oxidizing something else. So therefore
Mhm.
I am being reduced. Right?
Mhm.
These things, oh, the amount of times I hear, oh, a reducing agent gets reduced because of the word, and it's like, oh, no, no, right? Agents, something else. So make sure to be so, so careful when you see those terms or use those terms. Just think agent, something else, right? Therefore,
Yes.
I'm the opposite.
Yes, and that's so important. And I love that you also think of an agent like as a person who does
Yes,
something, because
right.
sometimes people don't.
Hmm.
I always visualize it that way. But I do think there's another important layer to this.
Hmm.
Um, when we talk about reactions, sometimes you'll see a reaction given, right, with two reactants, right? Something that has electrons to give up and something that will accept them, right? We have an reducing agent and an oxidizing agent, and then you'll see the products. And sometimes you'll get a question of like, which of the following was the reducing agent? And you'll see the two reactants and the two products. So I think it's important to clarify that when we talk about agents, reducing agent, oxidizing agent, we're talking about the reactants
Mm-hmm.
that want to oxidize and reduce each other. If
Mm-hmm.
we asked what has been reduced,
Mm-hmm.
right, you'd be looking at one of the products. What is the product of reduction,
Mm-hmm.
essentially? So
Mm-hmm.
you sometimes will get different language in those questions that are directing you either to the reactant that is willing to be reduced or
Mm-hmm.
oxidized, or the product that has essentially formed from reduction or oxidation. So
Yeah.
just be careful. Oxidizing agent, reducing agent, we're always talking about the reactants there.
Mm-hmm.
But then when we're trying to decide what is being asked about, we need to pay close attention. Are you asking about a reactant or more so a product?
Right, we have to be so careful and pay really attention when there's those like I like using the buzzwords in a question. Like be very careful how they word their questions because
Yeah.
I have seen way too many people and people call them silly mistakes. I don't think they're silly mistakes. I think you just genuinely
Mhm.
missed it. Like oh, I missed that they were talking about what was reduced rather than what was doing the reduction, right? Something along those lines. Like oh, I just missed that. No, we weren't paying attention. We were not knowing to look for these things. But I'm so glad that you brought that up so that everyone listening knows to be looking for those kind of
Yeah.
nuances there. And
Yeah.
so this is awesome, right? So when you know when a redox is happening, okay, we know how to label each one. What's the reducing agent? What's the oxidizing agent? We know the redox reaction. But I kind of want to kind of take it back to like the atoms themselves. What happens when they're reduced? What happens when they're oxidized? And this is where I think is a good place to talk about oxidation numbers, right?
Hmm.
The way I sort of think about oxidation numbers, and I'd love to hear your thoughts on this, is when an atom has bonds to it, has bonds connected to it, I kind of think about them as how many electrons in the bond does this atom own? Like how much of it does it own? Right? So imagine I have, I like talking about water, for example. Water is kind of, I think, the one to talk about a lot because water, H2O, is an oxygen bound to two hydrogens. Right? And so when we have that oxygen bound to two hydrogens, I like thinking about, okay, which one's more electronegative? The oxygen or the hydrogens?
Definitely oxygen.
100% the oxygens, right?
Definitely oxygen.
100% the oxygens, right? Those hydrogens, so not electronegative, not pulling any electrons towards them, right? That's electronegativity. I should maybe step back and define it, right? Electronegativity is the propensity of an atom to pull the electrons in a bond towards them. And so if I'm a hydrogen, I'm not pulling the electrons in the bond. The oxygen's really pulling it. So if I'm asking, okay, who in this atom owns the electrons in the bond, the oxygen versus the hydrogen, it's really the oxygen that really is owning those electrons. It's way more towards the oxygen rather than the hydrogens, right?
Yeah.
And so it's this idea when we think about oxidation numbers, how many electrons does this thing own in the bond? And so
Mhm.
when we think of that bond, okay, the bond between oxygen and hydrogen, those two electrons going to the oxygen, that means that extra electron, the oxygen starts out, 0, right? By gaining that extra electron, it gains that negative. So that single bond made that oxygen -1 and that hydrogen +1. But then in H2O, there's a second bond. So that still taking that extra electron away from the hydrogen, that adds another -1, and the hydrogen is a +1. So this is where we get that oxidation number of oxygen would be -2, and the oxidation number of hydrogen is +1. And this is a general trend that we see, when atoms, because we know oxygen's very electronegative. When it's bound to something, it's normally going to own those electrons. So
Yeah.
generally, when we see oxygen in a molecule, we say that its oxidation number, right, which kind of reflects how many electrons it owns, is -2. And hydrogen, very non-electronegative, right, is usually going to be +1. But there are some exceptions to this rule, right?
Yeah. I feel like it's important to clarify what we mean by own, right?
Hmm.
Because these are not my individual electrons that I'm oxygen. I don't want you thinking, oh, oxygen always has a charge of -2.
I see, yeah.
These are not my electrons. I'm not sharing them with anyone. They are shared. We're talking about shared electrons.
Hmm.
But again, within a bond, these electrons aren't like little individual particles,
Hmm.
right? You form this electron cloud on where that electron density is around these different atoms in that bond. What we're saying is most of that electron density is going to hang out right around
Towards
oxygen.
oxygen. Hmm.
So when we talk about how much it essentially has been, or its propensity to be oxidized or reduced, we're thinking how much electron density do you have around you?
Hmm.
So oxygen because it loves hogging that shared
Right.
electron density, has that -2, hydrogen has that +1.
Hmm.
And this is pretty consistent.
Hmm.
There are exceptions, but I feel like to give you guys just a frame of reference for things that don't have oxygen and hydrogen, right? If you are just one element,
Hmm.
that it's just you
Hmm.
and you're not charged, it's zero, right?
Right.
You're not sharing
Yeah.
those electrons with
Yeah.
anyone. Your oxidation number is 0.
So this is like
Um,
all your metals and stuff, right? Like Ag
yeah,
solid or, magnesium solid or sodium in
yeah,
the solid form. All of them, they're by themselves in the solid form, oxidation state of 0.
yes. But if you then took that metal,
Hmm.
right, and made it a metal ion,
Hmm. Hmm.
right? If you had oxidized that, right, because we lost electrons, making a positive charge, you created a positively charged metal cation, right? Now its oxidation number is pretty different, right?
Hmm.
The key idea is the oxidation number that you have as a molecule, right, is ultimately the sum of all the oxidation numbers of the atoms involved in that
Hmm.
molecule. So
Hmm.
if it's just you and you're, let's say, magnesium, and you become magnesium 2 plus,
Hmm.
right, your oxidation number has changed. If you went
Hmm.
from magnesium solid with an oxidation
Hmm.
number of 0 to magnesium 2 plus,
Hmm.
right, that might be water soluble, right? You now have an oxidation number of +2. You have been oxidized because you've lost
Right. Right.
electrons.
And it's this idea that the oxidation numbers add up to the charge of the whole molecule, I think is something that gets overlooked, but something I think is so critical. I think is the most critical aspect of oxidation numbers because you'll get those questions on the MCAT talking about, oh, what's the oxidation state of iron in this atom, for example. And then your
Mhm.
job is to be like, you might think, oh my goodness, I haven't memorized what iron is. What do I do? Right? But it's really coming back to the idea that all the oxidation numbers have to add up to the charge. Again, I always like coming back to water when talking about
Mhm.
oxidation numbers because we just talked about water, right? The charge of a water molecule is 0, and we know that, right? Because oxygen has -2, and there's two hydrogens, each +1. You add those
Mhm.
all up together, it adds up to 0. But then this is also in a lot of other places you were talking about before when atoms are by themselves, but also when they're bound to themselves. They'll also have an oxidation number of 0.
Mhm.
So take chloride gas, for example, like Cl2, right? As chlorine plus a chlorine, right? They're bound to itself. The oxidation state of chlorine here would be 0. O2, same
Yeah,
idea.
O2 also.
Oxygen bound to itself, oxidation state of 0, right? Because again, the total charge is 0, therefore neither of them can have a different oxidation number, so both of them must be 0.
Mhm.
Br2, N2, like anytime you see anything bound to itself, it's going to have an oxidation state of 2. It's when these atoms are in molecules with things that aren't itself, that's when you'll have these positive or negative. But again, oxygen generally is -2 when it's in a molecule.
Yes. And
Mhm.
hydrogen is typically +1. There are specific cases though that we actually can see hydrogen not be +1, right? If we thought of something like a hydride, like lithium aluminum hydride,
Mhm.
LiAlH₄,
Mhm.
right? You have two metals that we
Mhm.
know would rather be oxidized,
Mhm.
right? They're happy to give up those electrons. So when you have those two metals, lithium and aluminum, and then you put hydrogen in it, it's
Mhm.
a weird situation that hydrogen's actually
Mhm.
really more likely to
Mhm.
gain those electrons than the two metals they're bound to,
Mhm.
right? And therefore, that hydrogen is not a proton, it's a hydride, which
Mhm.
means it's a hydrogen that actually comes with both of its electrons,
Mhm.
which is totally different
Weird.
than it
So
normally
weird.
would be. Again,
Yeah.
normally it has a +1 oxidation number. In that case, it has a -1 oxidation
Mhm.
number.
Mhm.
So only when hydrogen is with something like a metal,
Mhm.
it may switch. Again,
Yeah.
oxidation of number of oxygen, pretty much always -2, unless it's with itself.
Mhm.
Hydrogen, pretty much always +1,
Mhm.
unless it's not a hydrogen, it's a hydride.
Mhm. Mhm.
And
I
again, the
think.
the hallmark there is if you're bound to other
Mhm.
metals,
Right.
basically.
And I think it really does come back to this idea that the oxidation states have to add up to the charge, right? Like, because
Mhm.
like the key foundation, like with lithium aluminum hydride, it's like, well, those will be positive, like the two metals will be
Mhm.
positive, and the whole charge is 0. So
Mhm.
you have to consolidate that somehow. So I
Mhm.
think like that's the big key idea, where they have to add up to the charge. So however you get there, you have to
Yeah.
get there.
And
And so, mhm.
and talking about the groups, just by the way, with metals,
Mhm.
if you're in group 1,
Mm.
something like sodium, you want to lose one electron so you get noble gas configuration. If you form a charge, right, you're going to be +1. You'll have an oxidation number of +1. If you were something in group 2, you'd want to lose 2, right? Like that's the rule. So like lithium, aluminum hydride, lithium wants to lose 1, right? Because it's in group 1. And then aluminum actually wants to lose 3. So it's +1 and +3. If you have LiAlH₄, you have +1 and +3, then
Positive 4.
among those 4 hydrogens, you have to get a -4 to get that all out to 0. So lithium is +1, Al is +3, and then each of those 4 hydrides has a -1. So just so you know, you can predict the oxidation numbers of basically all the metals except transition metals, which sometimes get a little bit of a headache, pretty easily just based on where they are in the periodic table.
Right. And I love that you kind of showed like how to actually find that, because I think that comes back to the idea, like me personally, I wouldn't want anyone to actually memorize the hydrides. That's just me personally, because you can find them using the charge of the oxidation state. That's where it's like, oh, don't try to memorize all your oxidation numbers. Like, don't try to do that. That's never the goal, right? The goal is that you understand the foundations, these ideas of, okay, it has to add up to the oxidation number, because as long as to the charge, because as long as you know that, most oxidation number questions you can do just fine, right?
Yeah.
And understanding the oxidation numbers and being able to calculate oxidation numbers is actually so critical for recognizing redox reactions, because this is kind of like one of the smoking guns that a redox reaction occurs. Because sometimes you're like, oh, did a redox reaction occur? Did it not occur? I'm not sure. Well, if an oxidation number ever changes, like an iron was a +2, then it became a +3 in the products, you know for a fact that a redox reaction occurred. As soon as oxidation numbers change, it definitely occurred. As soon as magnesium solid becomes magnesium aqueous and as the charge form, oh, redox reaction must have occurred. As soon as, we can do so many examples of atoms like iron 2+, iron 3+, that oxidation number has changed, it's occurred. We also see that in biological molecules, right? Take NAD plus to NADH, right? NAD plus to NADH. You've gained electrons there, right? And if you've gained electrons, NAD plus was reduced. Right? And so you see this again when I think about NAD and NADH. That's like, oh, that's from our metabolism. That's from aerobic respiration. We were talking about how we see those redox reactions, but as well, FAD to FADH2. You're also gaining these hydrogens, not protons, hydrogens, which have their own electrons that you're gaining. So because of that, that's also a redox reaction. You've also reduced the FAD, and then therefore there must have been some oxidation that allowed for that to happen. But so that's where you can see them in the atoms, but you can also see them in the molecules as well. So big smoking gun, if you see oxidation numbers change, probably redox reaction, or no, definitely redox reaction has occurred.
Yes. And I love that you bring in the biological application, because NAD/NADH2, NADH2, NAD and NADH,
So many hydrogens now.
FAD and FADH2, those are like, if you see those, boom, whether they're being produced or used, that's redox, period, game over. Like it's so nice when we look at this in a biochemical context. If it's Gen Chem, you need to be paying closer attention. Again, if you have a solid going to an ion, or if you have an ion that's changing charge, look closer. Again, just because we did, let's say, H2O to OH minus and H plus, that you see a change in charge, but there's actually no change in oxidation number there, right? Oxygen is still -2, hydrogen is still +1. In that case, you have H plus. Again, it's just a +1. It's equivalent to the charge. Cool. Oxidation number for oxygen is still -1 with the OH minus, right? H plus, or H in OH minus has +1. Overall is -1, right? That's not redox. So if you see NADH and FADH2, game over, you have redox.
Redox has happened.
It's like a hallmark. Same thing with NADPH, by the way, which is basically the same function. It's just more so used in anabolic or building chemical reactions rather than breaking and harnessing things for energy. But again, when we don't see things like NADH, FADH2, we just need to be more careful. That being said, there are so many biological applications of this, and they're pretty easy to recognize, either because NADH and FADH2 or NADPH are produced, or because we see we see the name of an enzyme that'll do it,
Oh my
right?
goodness. Enzyme names? Don't even get me started. We will talk about the enzyme names. Oh, don't get me started on enzyme names when it comes to memorizing. All the time, I'm like, hey, do you remember what this enzyme does? And people will blank. I'm like, just
Mhm.
look at the name. The name tells you everything you need to know 95% of the time. There is a
Yeah,
5% of very poorly named enzymes, I will admit that. But
yes,
95% of the time, the enzyme name tells you what it does, right? There's these
yeah,
triggers. Right? Sorry,
yeah.
I just felt very strongly there. I had
And
to
we will be talking about enzymes at some point in the future. In
near
the
or
pre-existed,
distant.
yeah. But if you see a name like oxido for
Mm,
oxidation, reductase for reduction, right?
yeah.
Or oxidase or reductase or
Mm,
dehydrogenase.
mm,
These are all another clue. And
mhm.
when we talk about metabolism later, you're going to see there are so many
So
applications of
many,
that, right?
so many dehydrogenases.
So
Oh my goodness.
yes. So
Mhm,
if you see specific enzyme names, redox, period.
mhm,
If you see
mhm.
NADH, FADH₂, or NADPH, that's a redox,
Redox, period.
right? Overall, when we look at aerobic respiration, when we
Mhm,
think glucose, C6H12O6,
mhm,
moving to CO2, that
mhm,
whole thing is oxidation,
mhm,
right? The whole process. Um, and then at the end, right, when we take oxygen and make water, that's
mhm,
a reduction process.
mhm,
Because again, if you think about it, O2, those both have oxidation numbers of 0. And
mhm,
now we're making H2O.
mhm.
That oxidation number for oxygen is -2, right? With those
Fantastic.
2 plus 1
Mhm,
hydrogens. So
mhm.
we do see redox reactions. That's basically what cellular respiration is. And
Huge
I feel
redox
like
reaction. Mhm,
at this point, it's important to recognize that in a biological context,
mm.
oftentimes, if you suspect redox, right, a big clue that yes, this could be is actually, and I hate this because it sounds like acids and
Oh,
bases,
what are you about to say? Oh, yes,
it
yes.
if you gain bonds to hydrogen
Mm,
or gain bonds to oxygen, that actually can be a good clue that you're being
mm,
either reduced or oxidized,
right.
respectively. So I know it, and this is the hard part. This is why people mix them up so much,
Right, right.
right?
This is what we were referring to before, right?
Mhm.
But I think the key difference is the difference between gaining a hydrogen and
And
gaining
gaining
a
a proton.
proton, right?
Yes.
I all the time I ask people, what an acid is, and they say, oh, it's something that gives away a hydrogen, and I'm like, no.
Not
We are
really.
stopping that right there.
Yeah.
We're not getting there because acids and bases, all, especially in the Bronsted-Lowry definition, all about protons. Whereas
Hmm.
redox, right? If you're gaining, losing hydrogens, right?
Hmm.
Then now this is a redox reaction, not acid base, right? And
Yeah.
that's why the name we actually just mentioned an enzyme name, a dehydrogenase, right?
Mhm.
Dehydrogenase. You are dehydrogening words hydrogening something where you're removing a hydrogen. You're not removing a proton, it's the hydrogen. So it's the proton with its associated electron. So it's the idea is you're removing the electron with it. Losing electrons, oh, you're oxidizing it. So
Hmm.
it's that nuance that we were kind of mentioning before, right? Like this, oh, we get it mixed up. We see these words, but that's why we have to be very careful with how we
Yes.
describe these reactions.
Yeah. So the key thing, and you're totally right, it's a proton versus a hydrogen.
Mhm.
I think a lot of students will look and be like, oh, this has an H in it. They
Oh no.
they're not always thinking, but that's why we
Mhm,
need to be extra careful. So
mhm,
biological applications, right? If you suspect redox,
mhm,
right, look very closely. Again, good
mhm,
hallmarks. If you have enzyme names, if you have electron carriers like NADH, FADH₂, NADPH, you're probably looking at redox,
mhm,
in which case the stuff that's bound to more hydrogens is probably more reduced. The
mhm,
stuff bound to fewer hydrogens or more oxygens is probably more oxidized.
mhm,
Again, you always want to double check that you truly do have redox reactions happening,
mhm,
so as not to get them confused with anything else.
mhm.
Um, but cellular respiration, again, glucose to
Great
CO2,
example.
that is all oxidation. Oxygen to H2O, that is reduction. You can verify if you want to with oxidation numbers. In fact,
That's
it would be
fun.
great practice.
Hmm.
But that's exactly what that is. And it's
Hmm.
kind of fun to talk about because I love evolutionary biology and
Oh no,
biology
don't talk to, oh no,
of
we're
other living things,
not.
talking about photosynthesis
Plants.
as essentially the exact opposite of
Mm,
cellular respiration,
Hmm.
Like it's so cool. You take, I
Hmm.
mean, plants breathe in carbon dioxide, which is what we breathe out, right?
Hmm.
And of course, they don't breathe, they don't have
Of
lungs, but
course.
still, right? They take in CO2 from the
Hmm.
environment and they reduce that
Hmm.
into glucose,
Hmm.
right? And in the process, they also take water, which is a metabolic byproduct for us, right? Everyone knows plants need water, but they take water and they oxidize it into oxygen.
Hmm.
So they are doing the exact opposite
Opposite, right?
of cellular respiration. Will you be tested on photosynthesis? No.
No, no.
But
It's cool.
it's super cool.
Oh my goodness, I love when evolutionary biology comes in. It's like, oh,
I just love it. It's
it's
so
just cool
fun.
stuff. It's just
It's
cool
just
stuff.
cool.
Right?
Yeah.
And so and there's again more than just like the, glucose and oxygen. We can even zoom into one of those really important parts of that pathway, right? Of aerobic metabolism, which is the electron transport chain.
Yep.
Oh my goodness, I love talking about the electron
Me
transport chain.
too.
We're
It's my
talking about
favorite.
redox reactions because it's like one of those things where everyone's like most people have heard of it before, maybe partially get it, but they don't really understand because we have to recognize what the name is telling us. We are
Mhm.
transporting electrons across these complexes. That means some molecules, some structures are gaining the electrons, some are losing the electrons. Wait a minute. We have
Mhm.
complexes that are gaining and others that are losing. This is just a whole bunch of redox reactions.
Yeah. It's like the most unbelievably phenomenal game of hot potato. Like, you get
What a
an
fun way to
electron
do
coming
it.
in from NADH and FADH₂, and these complexes are really just hot potatoing these high energy
Give it
electrons
away.
all around the membrane.
Hmm.
And I love talking about reduction potentials and
We're gonna
how these
talk about
processes. I know I have to curb myself. We
right.
may, wink,
Mhm.
wink, be
Mhm.
talking about this in a future episode.
Mhm.
There's a lot that we could talk about with the
Yeah.
electron transport chain, but for now, in our intro episode, right,
Mhm.
we just want to establish that electron transport chain is one giant chain of redox reactions. That's
Right.
exactly what it is.
Absolutely.
Um, and again, you can tell that because electron transport and also because the things delivering those electrons are NADH and
Oh,
FADH2.
immediately when you think them redox, like again,
Mhm.
brain is certainly already there, right? And I
And a
think
lot of those complexes have those enzyme names that we talked
right,
about.
yeah, like and like the complex one, for example, only has dehydrogenase in the actual name. And so it's like, oh,
Mhm.
everything's pointing to redox reactions, but some of us just like sometimes we just overlook, like I know I did. Like I when I first learned it, I'm like, oh yeah, electron transport chain, pumping protons, whatever, whatever. But then realizing that, oh, it's just a bunch of redox reactions. And
Yeah.
we're I'm feeling like, oh, I want to talk about so much more, like the ideas of coupling, favorable,
Yeah.
unfavorable, all
Yeah.
these
Yeah.
things, but
We will talk
we'll talk
about
about
it.
it. We'll talk about it later episode. Get excited for that one. But I think a really cool application of like, these redox things. I don't know about cool, but I think interesting is cyanide. We know about cyanide.
Mhm.
Cyanide is a very, very potent poison, right? We see it in like James
Mhm.
Bond movies, like, oh, they took a cyanide pill. The agent
Mhm.
like, silenced themselves. But we can talk about like the biochemistry of how it actually works. What
Mhm.
cyanide does is block complex 4, complex 4 being that last complex of the electron transport chain, which halts or stops the redox reaction. You can't keep redoxing anymore. So if you can't do complex 4 anymore, right, you can't, the electron transport chain is not going to work. And that's what leads to the fatality of cyanide because you're stopping those redox reactions from occurring, right? Which I
Mhm.
think, cool, a little bit morbid, but very cool.
Yes.
Right. And just to recognize how important, again, you stop one redox reaction and it's fatal. One
Mhm.
reaction, just one in your entire
Mhm.
body of 1,000 reactions, which again, fatal and morbid, yes, but also very intriguing science-wise.
Mhm. Right, because redox has the ability to power so many amazing reactions like ATP synthesis, right? That's
Hmm.
how you get the vast majority of your ATP from glucose,
Hmm.
right? That being said, those electrons, right, can also be very dangerous if they are
Hmm.
not properly like distributed to wherever they're
Hmm.
supposed to go, right?
Hmm.
If you don't have this nice pairing of, okay, this thing is reduced, this because this thing is oxidized,
Hmm.
if let's say you have an atom losing an electron or you
Hmm.
have what's called a free radical,
Ooh.
that electron is highly reactive and it
Hmm.
just wants to bombard whatever it can get its little tiny electron fingers on, right?
Hmm.
Most importantly, DNA, right?
Hmm.
It can damage things like proteins and mRNA and lipids and other things like that, but those are a lot less significant in many ways, right?
Hmm.
They're not irreplaceable. DNA
Right.
really is. And we actually have molecules in our body that are
Hmm.
designed to scavenge for those
Hmm.
free radicals
Hmm.
and accept them,
Hmm.
right? And these are called our antioxidants,
Right.
right? And I know we could talk for a long time because I know you have
Oh,
interesting
I can
things about
please let me
muscles.
bring it up. Please let me bring it up. Oh, I want to talk about it.
It's super cool, right?
Mhm.
Antioxidants are basically just absorbing those loose electrons
Mhm.
and preventing them from damaging other molecules.
Right. Can I talk about
Okay,
it?
go
Yes, I'm
for it.
gonna
Go
talk.
for it.
Yes, I love talking. It's so cool because a lot of the times, especially for the MCAT, we say like free radicals, like reactive oxygen species is another way that we can describe them, right? Do so much
Mhm.
damage because they really, really can to the
They
DNA.
do, yeah.
Right, absolutely. A
In
lot
some
of
cases.
But okay, a little bit of nuance there. Reactive oxygen species, a little bit actually is really good, especially if there's any gym frequenters out there, right? It's actually
Hmm.
really important for muscle synthesis because a little bit of damage in the cell is actually kind of a good thing because it signals that for growth, it signals that we need to kind of repair and build. I mean, that's why, some people go to the gym to damage their muscles so that we can repair them, grow. And actually, too many antioxidants is actually inhibits muscle synthesis. So, right, there are some important vitamins that we can talk about that are really important antioxidants, vitamin C and vitamin E, for example. So, in the muscle building community, like actually too much over supplementation with those is actually negative for muscle synthesis. So again, I say that as the MCAT's never going to test you on muscle synthesis and reactive oxygen species, the
But it's
relationship,
cool.
but it's cool, so we talk about it. You get to talk about evolutionary biology, I get to talk about muscle synthesis.
I
Yeah.
can agree with that. I can
Thank
agree
you,
with
thank you.
that.
And
I'll
I
shake
think
hands with you over
we'll
the
agree on that
camera.
one. But and I think it's cool because like I've heard of antioxidants since I was like a kid. Like I remember like my
Yeah.
parents be like, "Oh, have blueberries because they're full of
Blueberries,
antioxidants." Like,
yeah.
or I remember my
Go
mom
drink a
was like,
smoothie.
my mom's gonna kill me for saying this, but she was like, "Oh yeah, I sometimes have a glass of wine full of great antioxidants," which is true. A glass of
Yes.
wine is full of antioxidants. But again, I'd never known like why. Like we say it's good, but like why is it? It's because it helps to keep that cell safe from all that DNA damage.
Yeah.
But yeah, I think. But and again, the MCAT will expect us to know about our reactive oxygen species. Like when you see, ROSs in an exam, reactive oxygen species, can short form ROS. Like you see that in a passage, redox reactions. You want to be thinking antioxidants. You want to be thinking, okay, what's producing those ROSs? A lot of the times is aerobic respiration.
Yes,
Mhm.
absolutely. Right. And there are even more biological applications. We could get into
Oh
so,
my
so
goodness.
many,
Mhm.
right? We could talk about drug detoxification in the
Mhm.
liver, right? Especially when it comes to redox in like peroxisomes, for example, those little organelles that house a lot of our redox reactions. Um, cytochrome P450. We
Oh
could
my goodness.
there's a lot that we could go into. Again, there's so many different applications of redox reactions in the human body. Again, it's just like acids and bases. You're going to see this everywhere once you know what to look for, right? So
Mhm.
again, in the human body, look for NADH, FADH₂, NADPH. That's
Mhm.
absolute hallmark, right?
Mhm.
If you're thinking things like metabolism and electron
Mhm.
transport, that's a huge thing, right?
Mhm.
Those enzyme names, the oxidases, the dehydrogenases, the reductases, oxidoreductases, all of those huge hallmarks.
Mhm.
You will see this stuff in lots of passages. You could also see it standalone questions. You can see it in gen chem context. You could see it
Mhm.
in biochem and bio context.
Mhm.
This material is everywhere, right?
Mhm.
And we've talked about a lot of the macroscopic things, right?
Mhm.
It may benefit us to get a little bit more into the
Oh, to
micro
the
level,
microscopic, right?
more of
Into
the
like,
OChem.
oh, I know someone out there was just like, oh my goodness, the OChem.
Yeah, no,
Oh,
no, let's
or,
stay in bio. Mike and
no,
Molly, leave us alone.
we've got to touch on this because and it is
Yeah,
something we've actually already touched on a little bit already when it comes to redox reactions in OChem. But again, when we kind of pick it apart, I don't think it's actually that bad. So
it's not that bad.
stay with me, stay with
It's
everyone's.
not
Everyone's
that
like,
bad.
Mike, you're lying. Organic chemistry is the enemy. Like, no, okay, hey, just stay with
No.
us, right? It's not so bad. And
Yeah.
because again, recognizing when a molecule, again, looking at the shape of a molecule to recognize if it's reduced or oxidized, we were mentioning it before. When it comes to organic chemistry, we usually like to kind of look at the amount of bonds to oxygen and the amount of bonds to hydrogen. Right.
Hmm.
And so, all right, a lot of the times we look first, I like to start with oxidation, right? Like the oxidation of
Hmm.
something like an alcohol, because I think
Hmm.
that helps to conceptualize it first. Because when we
Yeah.
think about, an alcohol, right? Like say a primary alcohol, it has one bond to oxygen and that oxygen has a hydrogen, right?
Hmm.
But you can imagine if we oxidized that alcohol, What would you expect to happen?
So keep in mind, like you mentioned, right? If you're being oxidized, you're in a biological context, you're
Hmm.
typically losing bonds to hydrogen or gaining bonds to oxygen. So if we took an alcohol, right, which
Hmm.
is typically some sort of hydrocarbon, let's say, CH3, CH2OH,
Okay.
right? Ethanol, which
Mm.
is
I was
actually
like,
in your in your mom's glass of wine.
stop talking about my mom drink.
Right? A primary alcohol
Mm,
like ethanol, if
mm,
you oxidized it,
mm,
right, losing that electron, you're taking away that hydrogen with its electron, right?
mhm,
And you're actually going to create a carbonyl, right? You're going to create an aldehyde
mm,
in that situation. So you go from a primary alcohol to an aldehyde.
mhm,
And sometimes you could stop there if you just
mm.
oxidized it once or with one equivalent of whatever your oxidizing agent was.
Oh, we bring up
Um,
that word again.
I
Mhm.
know,
Mhm,
but keep in mind, oxidizing agent is something that would oxidize an alcohol into an aldehyde. In effect, it is being reduced.
mhm, mhm.
What would happen if we took it one step further?
Well, we just went from one bond to oxygen to two bonds to oxygen. Well, I mean, if my math is correct,
Why not more?
well, why not? Why not just one more? So we probably have one more bond to oxygen, and this is specifically, and this is only the case if we have a carbonyl at the end of the molecule, i.e., an aldehyde. This would
Hmm.
not be the case if we had a ketone. But if
Hmm.
we had an aldehyde, something that's a carbonyl at the end of our molecule that has the hydrogen bound to that carbon, we can add another bond to oxygen and turn that aldehyde into a carboxylic acid functional group, right? Because it has those three bonds to oxygen, the two on the carbonyl and that one extra on that OH group.
Yes. And we've been saying carbonyl, if that's a new term, it's a carbon that's double bonded to an oxygen. That's
Hmm.
what a carbonyl is,
Hmm.
right? So an alcohol doesn't have that. It's just a single bond to OH. An aldehyde does,
Hmm.
right? You take that same carbon that was COH, right? And you now take some of those electrons away. Carbon is double bonded to
Hmm.
an oxygen, as in it's a carbonyl, right? And then it has a hydrogen because we're at the very end of that molecule,
Hmm.
right?
Hmm.
What you mentioned with ketones is you have a carbonyl, but it's actually in the middle of a molecule,
Hmm.
right? So you don't have that double bonded oxygen or carbon to oxygen with the hydrogen. Now you
Hmm.
have two like R groups, two
Right.
carbon-based groups.
Right.
So you couldn't take that and become a carboxylic acid.
Hmm.
I think a lot of us have heard these terms before, but just in case we haven't, carbonyl, that's what we're talking about.
Right.
Um,
Right.
so we have these different reactions. What might be our oxidizing agents that we might want to
Mm.
use for a reaction like this?
So we've got a few different options depending on what our goal is. Like when I kind of imagine these, this kind of two-step, like alcohol to carbonyl, carbonyl, like that double bonded O to a carboxylic acid. I like thinking that one of those are really, really difficult to do, right? One of those
Yeah.
is much easier, one of those is much difficult molecularly to do. A carbonyl to a carboxylic acid is really hard to do, right? Molecularly. Whereas an alcohol to a carbonyl is a little bit easier to do. This fact alone is really important in determining what oxidizing agent we're going to use. Because maybe I just want to stop at the carbonyl. I want to go from alcohol to carbonyl. I don't want to keep on going. I don't want to use something that's really, really strong,
Yeah.
right? Because if I use something that was really, really strong, a really strong oxidizing agent, it will go from alcohol, carbonyl, and then not stop. It's going to keep on going,
Go all the way. Yep.
right? So I want to be using something that's actually a weak oxidizing agent if I want to stop at that carbonyl. And so that way, and for the MCAT, there's kind of like one weak oxidizing agent that you really, really need to know, and that is PCC. When you
Hmm.
see PCC, that is an oxidizing agent. That's all you don't need to know, like what PCC actually looks like. That's just the
Uh-uh.
name of it, right? And all you need to know is a weak oxidizing agent that can take an alcohol to a carbonyl. But since it's weak, it can't do that tough reaction of bringing that carbonyl to the carboxylic acid. But
Hmm.
say we did want to take that carbonyl to a carboxylic acid. We actually did want that carboxylic acid. We'd use much stronger oxidizing agents. There's kind of two I kind of think of like chromium oxide, CrO₃, and KMnO₄. What is that? Potassium permanganate. I think that's what it's.
Yeah.
Yeah, potassium permanganate and chromium oxide. Notice lots of oxygens, like it's CrO₃ and KMnO₄. When you see lots of oxygens, is generally a strong oxidizing agent. And so these are strong that will take it all the way to a carboxylic acid, whereas PCC, because it's weak, it can do that easy one of alcohol to carbonyl, but can't do that hard one of going from a carbonyl to a carboxylic acid.
Yes.
Hmm.
Yeah. And I think when we talk about that easier reaction, it's
Hmm.
important to identify that you can go from a primary alcohol to an aldehyde, or if you had a secondary alcohol, you could go to a ketone. Again,
Hmm.
that's when it's in the middle, right? If
Hmm.
the alcohol or the OH was bound to a carbon that had multiple carbons attached, right?
Hmm.
That's totally fine. You can do that as well. So it's not at the end of the group, it's in the middle. You can create a ketone. What if you had a tertiary alcohol? What would happen
Ooh,
there?
nothing.
If
Nothing.
you had a carbon that's attached to three different other carbon containing groups and then also an OH,
Nothing.
why could you not make that a ketone or an aldehyde?
What a great question, Molly. It's like I feel like you're like, all right, Mike, do you know the of course, right? It's because we don't have any hydrogens on that carbon to remove. And so I can't add another bond to oxygen there. Because again, a carbon can only have 4 bonds in total.
Exactly.
And a redox reaction can't break a carbon-carbon bond. It just can't do that. And so even if I have an alcohol and I add a really strong oxidizing agent, if that carbon doesn't have a hydrogen on it to remove, it's not
Can't
going to
be
go in.
oxidized.
It's not going to
Yeah.
go anywhere, right?
Yeah.
Hmm.
Yeah, I think that's super important. Again, you can convince these atoms or these molecules to react, especially with really strong reactants, really strong oxidizing agents.
Hmm.
But if it's physically not possible, again,
Hmm.
carbon can only have 4 bonds.
Hmm.
If that carbon is bonded to 3 other carbons and then an oxygen, how is it going to gain a fifth bond to oxygen? It
It can't.
can't do that. It just can't do it. Carbon wants to
Hmm.
bond 4. It can't do
Hmm.
that.
Hmm.
So it's important to keep in mind the limits, right? There
Hmm.
are some things that, you can add more and more power, more powerful oxidizing
Right?
agents, but you can't change the chemistry so it can react sometimes,
Absolutely.
right? So there are
Absolutely.
limits.
Absolutely. As in all things. And so, say, we've done this oxidation, we've gone to our aldehyde or ketone, we've gone to maybe our carboxylic acid, but just because we can go one way doesn't mean we can't also go the other way, right? Because
True.
so these where we used oxidizing agents to oxidize our alcohol carbonyl to our carboxylic acid. But say we want to go the other way. Well, if oxidizing has got us there, what would it be to go the other direction, you think?
It would be a reducing
Of
agent.
course, we would need a reducing agent to reduce it back the other way. And so when it
Yeah,
comes to reducing agent, I kind of like MCAT reducing agents because I think there's
me
kind of just
too.
two you need to know. And actually,
Mhm.
considering how much I know you love these ones, I'll actually take you because again, there's one term I've heard you say so much that you love more than anyone, which is just hydrides. You love
It's
hydrides.
hydrides.
You
We
love
love it.
hydrides. So I'll let you take this one away.
Well, we have mentioned hydrides before, right? I
Hmm.
brought them up actually kind of as an accident, not
Hmm.
even remembering that we were going to talk about this, but now we are. And here it is again,
Right.
accidental
Amazing.
repetition.
Hmm.
Right? We talked earlier about how with oxidizing or oxidation numbers, hydrogen is pretty much always +1,
Hmm.
except in a hydride, right?
Hmm.
Except when hydrogen, oddly enough, is really the most electronegative thing there. It is the one that I guess would contribute a negative charge because the others aren't going to do that,
Hmm.
right? And in this case, again, that hydride is donated with its electrons,
Hmm.
right? So if we want to reduce something, keep in mind that is going to be a process that, yeah, you're gaining a hydrogen, but you're also gaining the electrons associated, right? That is reduction, right? So our primary reducing agents that we'll talk
Hmm.
about that could take you from, let's say, a carboxylic acid to an alcohol or an aldehyde to an alcohol or a ketone to an alcohol or whatever it is, right? The two that we primarily are concerned with are our hydrides, right? There's
Hmm.
sodium borohydride, so
Hmm.
NaBH₄,
Hmm.
or lithium aluminum
Hmm.
hydride, so
Hmm.
LiAlH₄.
Hmm.
And that really is the stronger of
Hmm.
the two, LiAlH₄.
Hmm.
If I can spit it out.
Yeah, right. The,
Lithium
the the the
aluminum
words,
hydride.
it's a tongue twister, I swear.
It is. It really
Hmm.
is. Especially the reading out the letters. But that
Hmm.
is really the stronger of the two.
Hmm.
Um, that is really the only one that can take us all the way. If we wanted to go from a carboxylic acid
Hmm.
to an alcohol, right? You really need a pretty strong reducing agent that requires the LIALH₄.
Nice. Oh, you nailed it, that one.
Thank you.
It's kind of like, remember when we were talking about like juxtaglomerular cells and you just
Yes.
couldn't say
Hmm.
it. I
Hmm.
just thought about the tongue twisters. Anyway, sorry.
I
Let
know.
you continue on
There
please
are
continue. Yeah,
there are a couple, right? But
yeah.
again, like you mentioned, going from an aldehyde to a carboxylic acid is a pretty tough oxidizing step. To go from a carboxylic acid to an aldehyde is tougher, right? Especially if we want to go all the way from a carboxylic acid to a primary alcohol, it
Hmm.
requires the pretty strong one. If we wanted to do something like an aldehyde or a ketone to an alcohol,
Hmm.
that really doesn't require anything super
Hmm.
overpowered, right?
Hmm.
Sodium borohydride is fine with that. Of course, you could use lithium aluminum hydride if you want to,
Hmm.
right?
It's easy, right?
It's fine. Yeah, you could
Mhm.
do it. It certainly would give you enough power. But something like sodium borohydride is also perfectly fine for that kind of reaction.
Right, right. And
So
I think it's cool that like that transfer between a carbonyl and a carboxylic acid is tough in both directions, right? It's tough in
mm,
oxidizing, it's tough in reducing. And that's kind of why I always think, oh, it's kind of tough, so you need something really strong to do that. Whereas
yeah,
that alcohol to carbonyl, it's both in both directions, so you can use the weaker ones for that one.
yeah,
I just love that it's kind of like constant throughout. It'd be the worst if it was the opposite, but it's not.
I know. But again, it all has to do with stability of these
Of
different
course, of
molecules.
course, of
When we're
course.
trying to decide, will this reaction go forward?
Mhm.
How much do I have to prod
Of
this
course,
reaction to
right.
get it to go? Right? What do I have to do to kickstart this reaction?
Mhm.
Um, and I feel like that actually kind of is leading us into our next topic
Oh,
of discussion.
that
Right?
what a very clean transition. I swear, did you plan this?
I did
Wow.
not. I did not.
Mhm.
This has been my episode to stumble upon valuable transitions
Right, right.
and
Because
callbacks.
right, and callbacks. Right? Because this is
Yeah.
the idea that you talk about, like, does something happen? Does something not happen? Will it happen on its
Mhm.
own? Is there enough energy? What's the change in
Mhm.
energy, right? This is kind of, if you haven't guessed yet, our next episode is going to be really focused on thermodynamics and really linking it back to redox reactions, and we're going to be talking about electrochemistry, right? These,
Woohoo!
oh, I swear, I was almost going to say what there was something I was going to say. I was going to say it's the MCAT point machine. That's an insight.
It's an inside
You
joke.
had to be there. But right, this is the idea where our redox reactions, we need to understand how they relate to like thermodynamics, right? And the ideas of spontaneity,
Mhm.
of exothermic, endothermic reactions on entropy, right? Because they're so important, especially when talking about metabolism, especially when talking about electrochemistry, tying these things together will be so important. So we thought like after we talk about redox, we define oil rig or LEO-GER. Again, we're a LEO-GER podcast here.
Yeah.
Understanding how it relates to spontaneity, I think, is so, so critical.
Yeah, and I'm
Mhm.
really excited about electrochemistry as well.
Mhm.
I've taught the electrochemistry free class that we offer every once
Mhm.
in a while on our homepage so many times.
Mhm.
And I'll usually ask at the beginning of those free sessions, like, what are you hoping you'll learn today? Or like, how comfortable do you feel with this material already?
Mhm.
So many students are like, I literally hate this. Like, if you can
Right.
just make me hate electrochemistry a little bit less, I'll
Mhm.
call it a win. And I'm like, game on, let's do it.
Right. Well, actually, quite the
I love
opposite.
electro.
Well, I'll make you love electrochemistry so much because I think it's just generally cool. I think once you
It's
understand it,
cool.
like, because I think it's a little bit like, oh, when we're kind of scared of it, I there's this great
Mhm.
quote, like we're scared of the things that we don't understand. Like that's the only
Mhm.
things that we're scared of.
Mhm.
And so I think once after our electrochemistry episode, anyone listening who struggles with electrochemistry, oh, you're gonna love it. You're gonna love it. So
Yeah,
I'm excited. I'm excited for all of us, really.
me too.
Mhm.
Especially because I think electrochemistry is like it's the very highest up and most complicated that this idea of redox really gets for most
Mhm.
students.
Mhm.
And I think most people try and learn it
Mhm.
without having a foundation and understanding of what redox truly is. And as we'll talk next episode, what a reduction potential is.
Mhm.
And if you don't understand what we've talked about today, and then a little bit of what we'll get into next episode,
Mhm.
it's not impossible, but it's so
So
hard to
hard.
understand.
Mhm.
So what we're really doing is laying all the groundwork that you need to not only understand electro or I almost said electrochemistry, redox reactions as a whole and all of those biological applications. We've also really laid the groundwork for arguably one of the hardest general chemistry topics that is
Mhm.
testable on the MCAT. So
Mhm.
I am so excited, and we get to talk about thermo. So
Mhm.
it's going to be a great episode. I personally cannot wait. I hope you guys are excited for it. Definitely tune in.
Mhm.
And if you like these episodes, definitely, keep coming back.
Keep them back to you and comment. Tell us what you learned today. I would love to hear that. If
Yeah.
you learned something new, let us know. We feel so again. We look at the comments again. Molly and I were like send each other the comments. Like we see like
Yeah.
a cool comment, we're like, oh my gosh,
Like,
this
might
is
you
the
see this
best. Yeah,
one?
I know. I only got the message from you, and I was like, oh, that like made my day. So we love hearing from you. If you learned something new, if you're enjoying these podcasts, let us know. Or
Yeah.
come tune in to our free trial sessions. I know a lot of people tune in on those, so come join us. We have a
Mhm.
great time. But yeah, I guess with that.
Yeah.
Happy studying,
Let's,
everybody.
yeah. Happy studying. We'll catch you in the next one.
All right. Bye now.
Bye.